April 1945. The war in the Pacific was nearing its end, but every island still fought like the first day. On Okinawa, engineers attached to the United States Navy's Forward Technical Intelligence Unit were combing through captured airfields when they found something that didn't fit any manual, any known silhouette, or even any flight logic. The fuselage was small, barely 20 feet long, shaped like a torpedo with wings too short to glide and a cockpit too cramped for any pilot to bail out. The nose was solid steel, threaded for a massive explosive charge. The tail carried 3 exhaust ports. One of the men examining it, Lieutenant Robert C. Westbrook, wrote in his notebook, "No provision for landing gear. No fuel system in the usual sense. This isn't an airplane. It's a rocket, with a man inside it." The Japanese had called it the Yokosuka MXY-7 Oka, meaning cherry blossom. Allied troops, reading intelligence intercepts, already knew the name but hadn't believed the reports. They had heard of a rocket-powered glider that was released from bombers, guided by a human pilot toward enemy ships, and detonated on impact. But until they saw one in person, few believed it existed. The wreckage at Okinawa was the first largely intact example captured during combat operations. The Americans nicknamed it Baka, Japanese for fool. But the officers who ordered it crated and shipped back to the States for analysis didn't think it foolish at all. They thought it dangerous. The discovery triggered a priority-level intelligence alert. Within weeks, the craft was aboard a transport ship bound for the Naval Air Material Center in Philadelphia, where captured enemy aircraft were systematically evaluated. Alongside it traveled fragments of similar machines recovered at Kure and Kanoya, as well as the manuals and flight test sheets recovered from Yokosuka Naval Air Technical Arsenal. These papers revealed something few Allied analysts expected in 1945. The Oka wasn't a field improvisation. It had been designed under laboratory conditions, tested in wind tunnels, and built in factories with precision tools that the Allies had assumed Japan no longer possessed. When the crate arrived at the Philadelphia depot that June, technicians from the Bureau of Aeronautics unbolted the panels and found a level of engineering that stunned them. The cockpit was hand-welded steel with minimal gauges, altimeter, speed indicator, and oxygen flow regulator. But the control linkages were perfectly balanced. The wings were constructed from laminated wood with aluminum spars, an efficient use of dwindling Japanese material reserves. Most shocking were the engines. 3 Type 4 Model 1 Mark 20 solid-fuel rocket motors arranged in parallel, capable of producing a combined thrust of nearly 2,600 kilograms for 10 seconds. It wasn't much, but enough to accelerate the little aircraft to nearly 600 miles per hour in its final dive. The engineers taking measurements realized that, in aerodynamic terms, the Oka was among the fastest human-controlled craft of the war. Flight simulations suggested it could reach Mach 0.86 in a terminal attack, faster than many jet fighters of 1945. And yet, its wings were too small for sustained lift, and its fuel load too brief for any maneuver after ignition. Every number confirmed the same conclusion. This was a one-way weapon. Its pilot had 10 minutes of powered flight, and no way out. At the same time in the Pacific, American aviators were encountering the weapon firsthand. The first sightings came months earlier, in March 1945, during the battle for Okinawa. Pilots reported Japanese twin-engine bombers diving steeply, releasing small rocket gliders that accelerated toward ships at impossible speeds. On April 12th, USS Manard L. Abele was struck by one of them, an Oka, plunging into her deck and detonating its 2,600-pound warhead. The blast broke the destroyer in half, killing 84 men. It was one of the few times in history that a manned rocket weapon had destroyed a moving warship. When those reports reached Washington, the reaction was disbelief. No known Japanese aircraft could accelerate so violently or withstand the aerodynamic forces of a 500-mile-per-hour dive. Even German jet aircraft, like the Me-262, struggled at such speeds due to control flutter and compressibility. Yet, the wreckage from the Pacific left no doubt. The recovered airframes matched the design specifications in the captured manuals. Japan had built a rocket plane capable of near-supersonic speed, and they'd built hundreds of them. By July 1945, engineers from the Naval Air Development Center were already sketching cross-sections of the captured Oka for study. Their notes read like a mixture of technical awe and moral discomfort. "Control harmonization excellent," one report began, though the ergonomic layout suggests minimal concern for pilot survival. Another noted, "Stability characteristics remarkably good for such short-moment arm, indicates sound aerodynamic understanding." The aircraft's center of gravity, they discovered, was perfectly placed for dive stability. Its structure, though wooden, was calculated precisely to absorb rocket thrust without disintegrating. Whoever designed it, one engineer wrote, understood stress distribution as well as any Lockheed or Boeing team. In August, the Bureau of Aeronautics assigned the captured Oka an American designation, a T-22 Japanese rocket plane, and began drafting an evaluation summary for internal use. The document's conclusion would later circulate among defense contractors and universities studying post-war aeronautics. It stated plainly, the Yokosuka MXY-7 represents an advanced aerodynamic solution produced under primitive industrial constraints. It demonstrates the high technical competence of Japanese naval engineers despite material shortages and extreme operational desperation. The line struck everyone who read it. Technical competence amid desperation. That was the paradox. The Oka wasn't madness, it was mathematics applied to a hopeless situation. The Americans didn't admire what it was used for, but they couldn't ignore how well it had been built. The Philadelphia team completed their initial teardown by late August 1945, days after the surrender. What they had once dismissed as a myth was now a case study in wartime engineering. One that didn't just raise questions about enemy technology. It forced them to reconsider what advanced really meant when innovation was born from necessity rather than abundance. They would soon find out that what lay inside that wooden shell would challenge their assumptions even more. The rockets, the guidance fins, the compressed air steering. It was a machine that shouldn't have worked, yet somehow did. And in the process, it showed the world that even in collapse, Japan's engineers were still pushing the limits of physics itself. The captured Yokosuka Oka arrived at the Philadelphia Naval Air Materials Center in the first week of June 1945. Its crate bore stenciled Japanese markings, hurriedly overpainted with U.S. intelligence codes and the words, "Handle with care, explosive nose section." The technicians who pried it open expected crude workmanship, the kind of improvised machinery that late-war Japan had been reduced to. What they found instead looked like something from a laboratory, not a battlefield. The first surprise came when the airframe was lifted onto a dolly. It weighed just under 4,700 pounds loaded, less than half the mass of an F-6F Hellcat. The wings detached cleanly at the root, held in place by precision-cut fittings. "Excellent joinery," one engineer remarked. "This isn't field carpentry." The wood was a high-density hinoki laminate, bonded with resin similar to the American phenolic adhesives used in the mosquito bomber. The airframe showed no sign of hurried assembly. Every rivet head filed smooth, every weld bead even. They began removing panels in order. Under the skin, they found something even stranger: a pressurized oxygen cylinder feeding a simple pilot breathing system, compressed air bottles for rocket ignition, and a neatly wired control circuit linking the firing switches to the 3 motor nozzles aft. The blueprints recovered at Yokosuka identified these as Type 4 Mark I Mod 20 rocket engines, each producing roughly 800 kilograms of thrust for 10 seconds. Together, they gave the Oka a final acceleration close to 9 Gs at ignition, more than any human pilot of the era could sustain for long. The analysts ran the math again and again. Launched from a G-4M Betty bomber at 20,000 feet, the Oka's glide path covered 20 miles before the rockets even lit. Once ignited, it could close the distance to an Allied ship in under a minute. The calculated terminal velocity exceeded 575 miles per hour. Those numbers stunned the Americans. Only the German Me-163 Comet rocket plane came close, and that had been developed with a decade of aeronautical research and industrial backing. Japan, cut off from aluminum and high-octane fuel, had achieved nearly the same performance with plywood and compressed air. When the evaluation board convened on June 12, 1945, it included experts from NACA, the Bureau of Ordnance, and the Office of Naval Research. The room was full of men who had designed rockets, torpedoes, and early jets. Yet as they examined the Oka's systems diagram, the mood shifted from disbelief to grudging respect. One memo recorded the sentiment, "Contrary to initial reports, this is not a crude suicide glider. It is a precision-built rocket weapon displaying aerodynamic knowledge consistent with Western engineering practice." The Americans traced its design lineage back to the Yokosuka Naval Air Technical Arsenal, where Lieutenant Commander Mitsuo Ota had begun developing it in 1943. The original intent, documents showed, was to create a high-speed glide bomb that could penetrate carrier task force defenses. When Japan's supply of guided missile components failed, Ota substituted human control for radio guidance. It was a grim equation, brains in place of circuits. Technicians tested every component that could be safely operated. The firing switches worked. The rocket plumbing was sealed with flawless brazing. Even the pilot's control stick, mounted directly to the elevon linkage by steel push rods, gave smooth response across the full range of motion. It was, in the words of one report, an aircraft that did not know it was disposable. In the test hangar, Navy engineers reconstructed the launch profile using full-scale mock-ups. A Betty bomber would carry the Oka slung beneath its fuselage. At 20 miles from target, the pilot inside the Oka would activate the detachment clamps, glide until within visual range, then ignite the rockets for the terminal dive. The warhead in the nose weighed 1,200 kilograms, almost identical to that of a U.S. Navy Mark 13 torpedo. Impact at 500 miles per hour would produce an explosive yield far greater than any conventional bomb then in use. The data raised a chilling realization. If Japan had managed to deploy the Oka in large numbers, even a handful of successful hits could have changed the calculus of naval warfare around Okinawa. The rocket plane's range limited its deployment. The carrying bombers had to approach dangerously close, but its precision and speed made interception nearly impossible once launched. In several engagements that spring, U.S. radar operators had only seconds to respond between detection and impact. The hangar tests also revealed how close the weapon had come to being something else entirely. Its aerodynamic surfaces were stable at high subsonic speed, and the rocket arrangement could have powered a reusable test aircraft if refitted with retractable landing gear and throttle control. One NACA observer wrote, "Replace the warhead with a pressurized fuel tank, and this becomes a sound basis for supersonic research." It was an astonishing thought that a weapon built for one-way missions could have pioneered the next generation of jet flight. Through July, the dismantling continued. Each component was catalogued, weighed, photographed, and compared with known Japanese standards. The results overturned Allied assumptions about Japan's technical decline. Despite strategic bombing and shortages, the level of precision machining in the Oka's fittings rivaled American aircraft industry standards. Its control linkages showed tolerances within 1,000th of an inch. Even the rocket exhaust cones were cast with Venturi profiles that matched theoretical ideals calculated by U.S. rocket engineers. The only truly crude element was the cockpit. No armor, no radio, no ejection seat. It reflected the weapon's philosophy: complete sacrifice for single-use efficiency. Yet, to the engineers examining it, the distinction between crude and advanced blurred. The design was at once primitive in purpose and sophisticated in execution. It proved that technical brilliance could coexist with operational desperation. By late summer 1945, word of the Philadelphia analysis had reached NACA's Langley Laboratory and Wright Field in Ohio. Aerodynamicists began comparing the Oka's test data with American rocket plane prototypes. They found the little Japanese craft remarkably clean aerodynamically, its drag coefficient lower than expected for wooden construction. In wind tunnel simulations, it achieved laminar flow across nearly 40% of the wing chord, comparable to the P-51 Mustang. For the officers overseeing the evaluation, that was the most unsettling finding of all. In an aircraft that had no chance of returning, the engineers had still optimized for performance. It was as if they'd built a Formula One car to drive off a cliff. In the coming months, American test pilots would take what they'd learned from this wooden rocket and apply it to research aircraft built for survival, not sacrifice. But in that Philadelphia hangar, surrounded by fragments of Japan's last gamble, one realization was clear. The line between genius and futility is often drawn only by purpose, not by design. The engineers realized that whoever designed the Oka had likely studied Western aeronautical research long before the war, when Japan's aviation schools openly exchanged data with the United States and Britain. Then came the structure. Beneath the thin wood panels lay an inner skeleton of aluminum spars, interlocked like the ribs of a ship. Each joint was double reinforced, and even the access panels for the rockets were sealed with precision-fitted clamps. There was nothing haphazard about it. The tail control system used steel pushrods, expensive and heavy, but nearly immune to warping. The choice was deliberate. Wooden linkages could flex under rocket vibration, throwing off aim. Steel ensured absolute control, even for 10 seconds of flight. The rocket section itself drew the most fascination. American rocket scientists from the Bureau of Ordnance had been experimenting with solid propellants for years, but the Japanese formula used in the Oka's motors was surprisingly refined. Chemical analysis of fuel residues revealed a compound blend of potassium perchlorate, asphalt, and oil-based binder, stable, slow-burning, and almost smokeless. In laboratory tests, it burned with a clean blue flame that left minimal residue. The Americans realized that this was one of the first examples of a hybrid solid-fuel rocket optimized for visual stealth. At 500 miles per hour, that meant the weapon left almost no visible exhaust trail. More astonishing still was how the Oka's engineers had managed the problem of pilot control under extreme acceleration. At ignition, the pilot experienced nearly 9 Gs of force, enough to blur vision and immobilize muscles. Yet, the control surfaces remained balanced, requiring minimal input pressure. The secret lay in the aircraft's mass distribution. The warhead formed nearly half the vehicle's total weight, creating a natural stability that allowed the Oka to maintain trajectory even if the pilot blacked out momentarily. The Americans dubbed it passive accuracy. In simple terms, once pointed, it would stay pointed. To verify this, the U.S. Navy ordered a series of unmanned glide tests at Naval Air Station Patuxent River, using a captured Oka airframe fitted with telemetry instruments and launched from a modified B-24. The results stunned observers. Even without rocket propulsion, the wooden glider reached speeds exceeding 420 miles per hour before leveling out, responding predictably to every control command. In one report, the test officer wrote, remarkably stable through entire descent envelope. No signs of structural failure up to Mach 0.74 equivalent. Craft demonstrates aerodynamic integrity beyond expected limits. These tests confirmed what combat experience had already shown. The Oka's biggest weakness wasn't its design, but its delivery. To release one within effective range, the parent bomber had to approach within 20 miles of an Allied fleet, well inside fighter interception zones. Dozens of G-4M Betty bombers were shot down before they could ever launch their rocket planes. The engineering had outpaced the strategy. Back in Philadelphia, disassembling the control system revealed one final detail that left the engineers uneasy. The Oka's instrumentation wasn't crude at all. It had a functional attitude indicator, a precision airspeed gauge calibrated in kilometers, and a simple but effective electric firing control. There was even a backup manual ignition system, a pull cable that bypassed the electrical circuit in case of failure. Every mechanism showed the same discipline, reliability for the duration of a single mission. A memo circulated through the Naval Air Development Center that autumn captured the paradox in one sentence: "We have never seen such precision, devoted to a purpose so brief." The American analysts who handled the project were not immune to the moral weight of what they were studying. Lieutenant Commander Edward L. Perry, one of the engineers assigned to the disassembly, later recalled, "You couldn't help but admire the craftsmanship. And then you'd step back and realize that someone had designed this knowing exactly what it was for, that no pilot was coming home." That knowledge made the workmanship almost unbearable to look at. But the technical insights were undeniable. The Oka had proven that rocket propulsion and aerodynamic control could coexist in a human-guided vehicle. The principles discovered during its study, center of gravity control, dynamic stability, and high-speed airflow management, fed directly into post-war American research aircraft. NACA's later reports cite the Oka, alongside the German V-1 and Me-163, as pioneering examples of manned rocket vehicle design. By 1946, one of the Philadelphia engineers who'd worked on the teardown, Dr. Henry S. Winfield, joined a classified research team at Wright Field studying supersonic control behavior. His notes mention lessons from Japanese Oka tail flutter, an echo of knowledge carried forward from a weapon designed for despair into a science built for exploration. Yet, the story of how such a weapon came to exist, who conceived it, who built it, and why, would prove even more extraordinary than its engineering. The Americans knew the name of its designer, and when they began piecing together his life's work, they found a portrait of a man who had used his genius to serve a nation that was already collapsing. That story began 2 years earlier, in a laboratory at Yokosuka, where a naval engineer named Mitsuo Ota drew a sketch on thin tracing paper and unknowingly built one of history's strangest machines, an aircraft that could outfly its age but never outlive its purpose. He called it Oka, cherry blossom, because, he said, it would bloom briefly and vanish. The prototype took shape in late 1943. Built mostly of hinoki cypress and light alloy scavenged from wrecked aircraft, the first test model weighed barely 4,700 pounds. Its wings were small, its fuselage compact, but the heart of it, the triple Type 4 solid-fuel rockets, could push it to nearly 600 miles an hour. In a glide test above Sagami Bay, the craft proved astonishingly stable. One engineer noted, "Even without power, it rides the air like a bullet." Production began at Kasumigaura Arsenal in early 1944. Each airframe took barely 2 weeks to build, assembled by apprentices and craftsmen who thought they were constructing experimental interceptors. In truth, the weapon was designed for one-way flight. It would be carried beneath a Mitsubishi G-4M Betty bomber, released within sight of an Allied fleet, and then, under rocket thrust, dive at nearly supersonic speed toward its target. In the months after Japan's surrender, crates marked "Captured Materiel" Yokosuka Arsenal arrived at the Philadelphia Naval Aircraft Factory. Inside were pieces of the MXY-7 Oka. Cracked wooden panels, rocket nozzles, flight controls, and one almost intact fuselage, its hinoki skin still faintly aromatic. American engineers lifted each part as if unwrapping something both beautiful and unsettling. The first inspection reports were brief but stunned in tone. "Exceptional craftsmanship," one began, "aerodynamic design superior to expectations." The Americans had assumed these were crude suicide bombs, improvised and unstable, but the closer they looked, the clearer it became that the Oka was anything but crude. Its fuselage lines were mathematically precise, its control harmony nearly perfect. The engineers noticed subtle aerodynamic shaping in the tailplane, small adjustments to balance lift at high speed. The rocket tubes were machined from cast steel, lightweight yet sturdy enough to survive combustion temperatures above 2,000 degrees Fahrenheit. Even the cockpit, primitive by modern standards, had every switch labeled, every cable neatly routed. By early 1946, the Navy's Aeronautical Evaluation Board completed its full technical report. It read less like a condemnation and more like a tribute. Within the limitations of available materials, the MXY-7 represents an extraordinary grasp of aerodynamic stability in the transonic regime, it stated. Performance estimates suggest controlled dives exceeding 575 miles per hour. For reference, no American piston-engine aircraft of that era could safely dive that fast. What struck them most wasn't the speed. It was the balance between simplicity and control. The Oka was built from what Japan still had: wood, glue, and willpower. Yet somehow, its design solved problems American laboratories were still struggling with, like maintaining stability at near-sonic speeds, where drag and airflow compress into chaos. At Langley, NACA scientists compared the Oka's data against their own wind tunnel tests for the Bell X-1, the rocket plane that would one day break the sound barrier. The results aligned disturbingly close. In an internal memo, one engineer wrote, "Stability curve parallels those predicted for high-speed transonic models. Recommend further study of Japanese methods for low-cost, high-strength wooden construction." What they meant was simple. The Oka's creators, working with hand tools in unheated workshops, had built something that behaved like a research rocket, an aerodynamic bridge between the age of propellers and the age of jets. They studied its lightweight bonded wood construction for prototype drones. Even the simplicity of its firing and guidance system influenced later design thinking: minimal electronics, maximum reliability. The irony was unmissable. A weapon built for self-destruction had ended up helping to make safer, faster machines. By 1950, pieces of the Oka sat quietly in research archives, their data absorbed into the DNA of American aerospace design. And while few ever said it publicly, those who'd handled it remembered the feeling, admiration mixed with a kind of sorrow. Lieutenant Commander Edward Perry, the same officer who first examined the aircraft in Yokosuka, summed it up best in his final report. "This machine stands as proof that even in collapse, discipline of design endures. It is impossible to study it without seeing both the brilliance and the futility of its creation." Years later, in 1961, when one of the few surviving Okas was restored at the Smithsonian, curator Paul Garber noted something that no report could capture. Running his hand along the smooth hinoki paneling, he said quietly, "They built it as if it would last forever, even though it was meant to last only seconds." That sentence became the most fitting epitaph the Oka would ever have, because, in the end, It wasn't the rocket motors or the numbers that defined it. It was the paradox it carried, the precision of genius in service of despair. The cherry blossom had bloomed for an instant, vanished in flame, and left behind a lesson that endured. That technology is never good or evil by nature. It only reveals what a nation chooses to make of it. For America's engineers, the Oka became a reminder of what to build and what never to build again. Thanks for listening till the end. I put a lot of effort to bring you factually correct and lesser-known stories of the past. Subscribe my channel if you like this type of content.